Hi everybody. Today I will present the chapter 11 in reinforcement learning book of policy methods with approximation. This is the outline for my presentation, and first I will revise on policy and off policy learning methods. Next I will present the challenges in the off policy approximation, and finally it is approximation algorithms for off policy learning. First, I will compare the on-policy and off-policy learning. For on-policy, the example is SASA, and for off-policy, the example is Q-learning. The update rule for the on-policy learning is based on the target policy that derives from the Q function, and for off-policy, it will rely on the behavior policy other than the target policy. The advantage of the on-policy learning is very easy to implement, and the algorithm converts faster. The pros for off-policy learning is very powerful and provide more exploration. The cons for on-policy learning is less exploration, and for off-policy learning is hard to implement. The algorithm converts slower and less stable. Now I will present a little bit about approximation. The question here is when and how do we need the approximation? When we apply the reinforcement learning for a very large-scale problem, sometimes we cannot represent the value function by a lookup table. At that time, we need the function approximation. And how we can do that? We can do that by replacing the lookup table for value function by general parameterized form. For example, here we can estimate the state value function and action value function by the parameterized form. This is the steps for approximation. And to do approximation, first we have to choose the approximator for this value function. It can be linear function, nonlinear functions, or neural network. And then we have to choose a criteria to evaluate our function. Finally, we can learn the parameter. However, there are some difficulties in off-policy approximation. There are three components that they are unstable, and it is most unstable if we combine them. The first one is function approximation to generalize the value function. The second one is bootstrapping, and the final one is off-policy training. And in off-policy approximation, we have to combine three of them, so the problem will be the method will be very unstable and challenging. Now I will present some methods for off-policy approximation. The first one is the semi-gradient method, and this method for off-policy learning is just like the corresponding on-policy algorithm, except for the addition of row. For state value function estimation, we can have the update rule like this, with the additional of row, where row is an important sample ratio and the delta is the temporal reference. We can also do the similar thing for the action value function by replacing the state value function by the action value function, and we can have a similar update rule. However, the semi-gradient method for off-policy approximation is unstable. For example, we have two states, one action with no reward, and we assume that we estimate the value function is w and 2w. So by using the semi-gradient, we can have the temporal difference by this equation, and finally we can achieve the update rule like this. But for if the discount gamma is greater than 0.5, we have this factor is greater than 1, so the W will diverges. Another example to show that semi-gradient method is very unstable. For example, we have seven states, and we have two actions represented by the solid line and dashed line. And for example, the value inside each state is the estimated value for each state. And by doing the semi-gradient update, we can have the result that all the parameters will not converge. It will increase forever. Another method for the off-policy approximation is PBE. It is a projected Bellman error on the space that represented by the function approximator. So in this method, our objective is to minimize the PBE. And finally, we can have the update rule like this. And the result for this function, this method is more robust than the previous one. As you can see in the result, all the parameters will converge, and also the error will converge. Another method for off-policy approximation is emphatic TD method. This method is a semi-gradient with the emphatic parameter m. We have additional parameter here, where m is represented like this, with I is a hyperparameter for interest, and it is arbitrary. As you can see in the result, although in the beginning of the step it is fluctuate, but finally the parameter will converge, and also the error will converge. This is the conclusion for my presentation. The first one is off-policy approximation is very, very powerful but very unstable and challenging to compare to on-policy approximation. Although the gradient TD and emphatic TD methods are more robust, but for some problems it might not work and very unstable. This is the end of my presentation. Thank you for your attention.